Hello. In the last lecture, I have introduced you to the uniform convergence and many other theorems. And we are going to extend the uniform convergence to stochastic functions. So it becomes more and more complicated, and everything becomes more general and abstract. But the main key idea is the same. So simply I will consider sample mean. So first, think about a function g that depends on a random variable omega I and a parameter theta, and we will consider its sample mean. So depending on the random variable, the sample mean of the function can take different values. So in that sense, gn hat is random. Gn hat is a random object that also depends on the theta. So it's a random function of theta. And we know that by the weak lobe large number under very mild assumptions, weak lobe large number implies that this guy converges in probability to G0. G0 is another function which is defined as the population mean of G. And this convergence is quite obvious. It's a pointwise convergence in probability. But as I said in the last lecture, remember, pointwise convergence in probability is not enough to think about a composite sequence. So if theta also is a sequence, then Gn and theta n may not converge to G0 theta 0 under the pointwise convergence in probability. So we have to strengthen the pointwise convergence assumption to the uniform convergence assumption. And you remember the uniform convergence without randomness was defined in this way. So the even the slowest convergence rate will converge to zero. So supremum, even at the point where the difference is the maximum, still it will go nicely down to zero. And here that same thing, you can do the same thing, but the only difference is convergence is in probability. So the maximum difference between the sample mean function and population mean function converges to zero. So the g theta may be a random function which may have a lot of errors, but the errors should shrink to zero as n increases and uniformly. That means the error should move together. They have to converge to zero at a uniform rate. So this is the definition of uniform convergence. And then, okay, it is nice. The definition is okay, and we know why we need it. And then how do we prove that? The proof of this uniform convergence is much more difficult than non-stochastic case. So here is a lemma. Uniform lobe large numbers. Think about sample mean function, and for this to be uniformly converging to a population mean function, then the sufficient conditions are: first, the parameter the parameter belongs to a compact set. And second, each function is continuous, almost surely, and the supremum, the maximum of the function must be bounded. So you may think this as a generalization of the weak lobe large numbers. So where is it? So in the weak lobe large numbers, you need expectation of the absolute value is finite, and we replace this assumption to uniform boundedness. So the supremum that assumption is replaced by, where is it? Replaced by supremum of the absolute value of the function. So the expected value is finite. So we take supremum. That's the difference. And then under these assumptions, we have the desired uniform convergence. To put a little more, by the way, the first two assumptions are required to guarantee that the maximum, the supremum, is unique. It's uniquely defined under these two assumptions. So otherwise, we may have this kind of problem. So this problem happens because the function is not continuous. So the discontinuity causes this kind of problem. And those are, so this is violated in our previous example. That is why the result is not true. And what else? And then as I said, what we want here is we would like to combine the sequence of sample mean function and a sequence of parameter estimator. So parameter value and the composite sequence converges in probability to this under the assumptions that first the random function uniformly converges to the limit, and the parameter sequence converges in probability to the true parameter theta 0, and the limit function must be continuous at theta 0. So these three conditions are exactly the same, exactly what we need. Where is it? What we needed here. Identical assumptions, only changing the convergence concepts to stochastic convergences, and everything else being the same. And then we have a nice result. Exactly, this is what we wanted to have. So I so far this is so far I have given you a lot of theories, but still you may think it's difficult, but I'm surely I can say that it's very mild version of the real theories. So if you are interested in econometrics, if you are interested in majoring in econometrics, you should know more than this. So this is the bare minimum for an econometrician to understand. And so if you are interested, like try read Nguyen McFadden. And there is a more generalized concept, stochastic continuity. This is basically a kind of continuity which it's similar. It means something similar to uniform. So and stochastic random. So stochastic uniform continuity. Um, and then if you could understand this, then you are good to major in econometrics. But I know that many of you are not interested in this, so I did not go deeper. But it does not imply you don't need to know that. But so if you major in econometrics, you need to know more details. So as a conclusion, in sum, so what we want here is for these to converge in probability to this, you need four assumptions. I'm just combining these assumptions and these assumptions. So some are overlap, like continuity is overlap, and these four assumptions are what we need to prove this convergence. So far, I have presented the preliminary theories, lemmas, and we are going to use those theories to prove the main results like consistency and asymptotic normal distribution and sampling distributions. So we are going to do that in the next video.